December 31st, 2026. Somewhere off the Oregon coast, a mile beneath the surface of the Pacific, a volcano is holding a deadline it did not agree to. Scientists studied its behaviour for 2 decades, watched it swell like a balloon, and did something almost unheard of in their field. They published the date by which it will erupt. They have been right about this volcano before, once, to within 7 months. But their deadline is now 4 months from expiring. The mountain is fuller than it has ever been measured, past the exact level that triggered its last eruption. And instead of accelerating, it is going quiet, slower, calmer, as if it knows. Tonight, we open the file on the only volcano on Earth with an expiration date, the machine watching it, the sealed prediction no one may read, and the question of what happens when the clock hits 0. Before we go any further, if you enjoy what we do here at Project Nightwatch, hit like and subscribe so you don't miss any of our nightly debriefs. Also, drop a comment and tell me where you're watching from. Let's get into it. Part 1. The Volcano with a Deadline. There is a volcano in American waters with an expiration date, not a metaphorical one, not a vague geological shrug of sometime in the next 10,000 years, an actual published on-the-record forecast issued by named scientists at real institutions that says this volcano will erupt before the end of 2026. You can go read it today, and as of tonight, that deadline has a little over 4 months left on it. The volcano is called Axial Seamount, and there is a decent chance you have never heard of it, because it does one thing that keeps it off every list of famous volcanoes. It hides. Axial sits about 300 miles west of the Oregon coast, and its summit is roughly 4,600 feet below the surface of the Pacific Ocean. That is nearly a mile of seawater sitting on top of it. No plume of ash will ever rise from it into a blue sky. No evacuation order will ever be issued for it. If you chartered a boat and parked directly above the summit on the day it erupts, you would see nothing but grey swells rolling to the horizon. The ocean does not even ripple, and yet by the standard that actually matters to volcanologists, how often it erupts, Axial is the most active volcano in the Pacific Northwest, and arguably the most active volcano in the United States. It has erupted 3 times in the modern instrumental record, 1998, 2011, and 2015. Mount St. Helens has managed 1 eruption and 1 long dome-building episode in that same stretch. Rainier has managed nothing at all. While the famous peaks of the Cascades sleep under their glaciers and their monitoring networks, this anonymous mountain of black basalt a mile under the sea has been quietly running the most reliable eruption schedule in North America. The reason Axial erupts so often comes down to an accident of plumbing. The volcano sits at the meeting point of 2 magma-generating machines. It is a hotspot, a persistent upwelling of hot mantle rock, the same kind of feature that built the Hawaiian Islands, and that hotspot happens to sit directly on top of the Juan de Fuca Ridge, a mid-ocean spreading centre where the Pacific Plate and the Juan de Fuca Plate are being pulled apart. Spreading ridges make magma on their own. Hotspots make magma on their own. Axial gets both supplies at once, feeding a shallow reservoir under a summit caldera. The mountain itself is enormous by any normal standard. Its rift zones run about 50 kilometres, some 30 miles to the north and south, and its flanks fall away to nearly 2,500 metres depth. Only the mile of ocean above it keeps it anonymous. It was not even discovered until surprisingly recently. Systematic mapping and submersible work in the 1980s revealed the caldera and its hot springs, and by the late 1990s the National Oceanic and Atmospheric Administration had made Axial the site of the first dedicated underwater volcano observatory. An early scatter of instruments called the New Millennium Observatory, deployed and recovered by ship, storing their data in memory until someone came back to collect it. That early network is how the 1998 eruption was caught at all, and it taught researchers the volcano's basic trick. But it watched the volcano the way a trail camera watches a bear, in snapshots, discovered after the fact. What exists at Axial today, and what makes tonight's story possible, is something else entirely. A live wire. That reliability is the entire story tonight, because a repeating volcano is a predictable volcano, or at least that was the idea. Somewhere in the early 2000s, researchers noticed that Axial does something almost no other volcano on Earth does so cleanly. It inflates like a balloon, on an almost mechanical cycle. Magma seeps up from below and fills a reservoir beneath the caldera, and the seafloor physically rises year after year, sometimes by more than 2 feet between eruptions. Then the volcano erupts, the magma drains out, and the floor of the caldera drops back down. In 2015, it dropped almost 8 feet in a matter of days, and then the filling starts again. Rise, erupt, fall, rise, erupt, fall. A geological piston, cycling away in the dark. 2 scientists have spent the better part of 2 decades measuring that piston. Bill Chadwick is a research associate at Oregon State University's Hatfield Marine Science Center in Newport, Oregon. Scott Nooner is a professor at the University of North Carolina at Wilmington. Together they have done something that sounds, on its face, almost like hubris. They forecast eruptions, publicly, with dates, before they happen. In a field where the standard answer to when will it erupt is a careful lecture about probabilities and uncertainty, Chadwick and Nooner put numbers on a calendar and let the volcano grade their work. And here is the part that makes Axial different from every scientist's warn headline you have ever scrolled past. They have been right before. In 2014, they went on the record saying Axial would erupt in 2015. 7 months later, it did. Not within a decade. Not within a margin of error the size of a career. 7 months of lead time on a specific volcano, and the mountain delivered. It remains one of the only successful long-range eruption forecasts in the history of volcanology. So when those same 2 scientists issued a new forecast, first that Axial would erupt by the end of 2025, and then, when that deadline came and went, a revised forecast of before the end of 2026, that was not tabloid noise. That was the most credible eruption prediction on planet Earth, issued by the only team with a confirmed win, about the only volcano wired up thoroughly enough to test it. Right now, tonight, Axial Seamount is the only volcano on Earth living under a public, dated scientific eruption deadline. Which brings us to the reason this is tonight's story, because the situation out there has developed a twist that nobody, including the forecasters themselves, quite knows what to do with. The volcano is ready. By the one measure the whole method is built on, it is past ready. The seafloor has re-inflated beyond the level that triggered the last eruption. The magma reservoir is as full as it was the day in April 2015, when 8,000 earthquakes tore through it in 24 hours and the caldera floor fell out from under itself. Every precondition the pattern demands has been met. Consider what that means for a moment, because it is worth sitting with. Volcanologists divide the world's dangerous mountains into categories of readiness, and the scariest phrase in the discipline is critically loaded. A system where the pressure already exceeds what broke it last time, where the question is no longer whether the load is sufficient, but only what finally lets go. By the logic of its own history, Axial crossed into that territory quietly, sometime around late 2025, when the rising caldera floor climbed past the level where the 2015 eruption began. No press conference marked it. A line on a pressure plot simply drifted above another line, 300 miles from the nearest witness, and the volcano is slowing down, not accelerating toward failure, the way a textbook would draw it, not swarming with earthquakes. The rate of inflation, the speed at which the seafloor is rising, has been cut roughly in half and then cut again over the past year. The earthquake count, which ran above 2,000 a day in the months before the 2015 eruption, is limping along below 100 a day. The scientists watching the feeds describe the volcano, in the same breath, as fully re-inflated and not imminent. Both of those things are true at once, and that contradiction is the deepest question in this entire story. Because one of 2 things is happening 300 miles off the Oregon coast right now. Either Axial is in the final quiet stretch before it proves that human beings can put an eruption on a calendar, a result that would ripple far beyond one seamount into every city on Earth that lives under a dangerous mountain, or the most closely watched volcano in human history, wired with more than 140 instruments, monitored in real time through hundreds of miles of fiber optic cable, studied by 2 of the best forecasters alive, is about to demonstrate that even under perfect conditions, a volcano can still look its watchers in the eye and refuse to follow the script. There is also a third clock ticking in this story, one almost nobody outside a small community of oceanographers knows about. The machine that makes any of this possible, the cabled observatory that carries Axial's heartbeat to shore, very nearly went dark this summer, not because of the volcano, because of a budget line. We will get to that, because the fight over those cables in June of 2026 may end up deciding whether anyone is watching when the answer finally comes. But first, you need to understand the strangest idea in this whole affair, the idea that an eruption can be scheduled at all. Because the method behind that deadline is so simple, you can hold it in one sentence, and so fragile that it has been wrong every year since its one great success. Part 2. How you schedule an eruption. The method starts with a measurement that sounds impossible, detecting the seafloor rising, a mile underwater, by fractions of an inch. The instruments that do it are called bottom pressure recorders. The physics is almost embarrassingly simple. An instrument sitting on the seafloor feels the weight of the entire column of water above it. If the seafloor rises, even by a centimetre, there is now 1 centimetre less ocean overhead, and the pressure drops by a precisely known amount. If the floor sinks, the pressure climbs. A good bottom pressure recorder can resolve changes at the level of a centimetre of vertical motion. In effect, scientists turned the crushing weight of the Pacific Ocean into a ruler. At Axial, those recorders are planted at the centre of the caldera, the volcano's summit depression, a bowl roughly 5 miles long and 2 miles wide, its floor about 300 feet below the rim, and out on the rim itself, and at more distant stations for comparison. The centre of the caldera sits directly above the magma reservoir, so it moves the most. The rim stations move less. By comparing centre against rim, day after day, the researchers extract what they call differential uplift, how much the heart of the volcano is swelling relative to its own edges. That differencing also cancels out tides, weather systems, ocean currents, instrument drift, everything except the volcano itself. The noisy breathing of the sea subtracted away, until what remains is the slow push of magma from below. And what 2 decades of that record shows is the piston. Between eruptions, the caldera centre rises steadily, the reservoir refilling at rates that have ranged from a few inches a year to more than 2 feet a year at its fastest. During an eruption, the floor collapses downward almost instantly as the magma drains out and races into the rift zones. The 2015 eruption dropped the centre of the caldera by 2.4 metres, nearly 8 feet, in about a day. Then the cycle resets, and the slow rise begins again from the new, lower floor. Getting that record took more than dropping instruments overboard, and the history matters, because the length of the record is the method's whole authority. In the early years, before continuous cables, the measurements were campaign-style. Nooner and colleagues would return by ship season after season, lowering a calibrated mobile pressure recorder onto the same seafloor benchmarks, concrete pads planted in the caldera, to remeasure their depth against reference stations, building the inflation curve one expedition at a time, the way surveyors re-level a mountain road year after year. Those repeat surveys are what first stitched the 1998 and 2011 eruptions into a single narrative of fall and refill. When the 2011 eruption struck, announced, like its successors, by an earthquake swarm and a sudden drop of the caldera floor, the record was finally long enough to test the boldest version of the idea, that the height of the floor at the moment of eruption was not an accident but a property. The 2011 event had fired at almost exactly the level reached before 1998. 2 cycles, 1 trigger height. That was the moment a research program about measuring a volcano became a research program about predicting one. Here is the leap of faith that turned that record into a forecasting method. When Chadwick and Nooner lined up the cycles, they noticed the eruptions were not being triggered at random heights. Each eruption seemed to fire when the caldera floor climbed back to roughly the same level it had reached before the previous eruption, as if the volcano had a structural failure point, a pressure at which the rock sealing the reservoir gives way, over and over, at close to the same load. They call it the inflation threshold. Think of a pressure relief valve on a boiler, set at the factory to pop at a specific reading. Fill slowly or fill fast, it does not matter. When the needle touches the line, the valve opens. If that is really how Axial works, then forecasting an eruption stops being prophecy and becomes arithmetic. You know the height of the line because the volcano showed it to you last time. You know where the floor is today because the pressure recorders tell you every 20 seconds. Divide the remaining distance by the current rate of rise, and the calendar produces a date. That is the entire method. No oracle, no supercomputer. A ruler made of seawater and a straight line drawn into the future. Notice what this method deliberately ignores. It does not care about the chemistry of the magma. It does not model the temperature of the reservoir, the strength of the roof rock, the geometry of the conduits. It treats the volcano as a sealed system with exactly two observable properties, how full and how fast, and bets everything on history repeating. Scientists call this pattern recognition, and they use the term with a self-aware wince, because pattern recognition is what you do when you cannot yet do physics. It is the almanac stage of a science, the stage where you can say the river floods most years in April, without being able to say why this year it waited until June. Every mature forecasting discipline, weather above all, began exactly here, and the question hanging over Axial is whether volcanology can make the same leap weather made when it traded folklore for fluid dynamics. Keep that in mind for later, because in the final act of this story, someone tries to make that leap in real time, on this volcano, with a model that does do the physics, and what they did with their predictions is one of the strangest and most honest decisions in modern science. In 2015, the arithmetic worked. The years before that eruption were the method's dream scenario. Magma was pouring into the reservoir at a ferocious, steady rate, about 70 centimetres of uplift per year, more than 2 feet, and the line on the plot ran straight as a rail. In September 2014, at a scientific conference, Chadwick and Nooner did the division in public and said, 2015. On April 24, 2015, the volcano erupted. We will spend the next part of this story inside that night, because what the instruments recorded in those 24 hours is still, a decade later, the single best recording of a volcanic eruption ever made. But before we go there, mark the two numbers that everything later in this story hinges on. First, when the 2015 eruption fired, the caldera floor was about 30 centimetres, roughly a foot, higher than the level that had triggered the 2011 eruption. The threshold, in other words, was not perfectly fixed. It had drifted upward. The valve popped a foot late, if you want to think of it that way. So the honest version of the method became, the next eruption should trigger somewhere between the 2015 level and about 30 centimetres above it. A band, not a line. A danger zone painted on the pressure gauge rather than a single tick mark. Why would a threshold drift upward between cycles at all? The candidate explanations are themselves a tour of what nobody knows about volcanoes. Perhaps each eruption anneals the reservoir roof, heals old fractures with fresh rock, leaving the lid slightly stronger and demanding slightly more pressure next time. Perhaps the reservoir geometry shifts as repeated drainings and refills rework its shape, changing how pressure translates into uplift. Perhaps the threshold is constant in stress but not in centimetres, and the conversion between them wanders with the temperature and gas content of each new batch of magma. Any of these stories fits a foot of drift. None of them can be tested from above. The honest engineering summary: the valve exists, its setting creeps, and the direction of the creep, upward so far, has bought the volcano extra silence each cycle. Second, as of this year, the caldera floor has already climbed about 10 centimetres above the 2015 threshold. It is inside that band now, with perhaps another 20 centimetres of headroom before it exits the top of the zone. Hold on to that. The volcano is not approaching the territory where its last two eruptions began. It is standing in it. It is worth being precise about why this works at Axial, and almost nowhere else, because the exception proves the rule. Most volcanoes are terrible balloons. Their magma systems are tangles of stacked chambers, sills and conduits. Their edifices are heaps of rubble and old lava that deform unevenly. Their eruptions tap different reservoirs at different depths, so no two cycles look alike. Axial is geologically simple in a way land volcanoes almost never are. One shallow reservoir, imaged by seismic surveys directly beneath the caldera. Hot, fluid basalt that flows rather than clogs. A fast, continuous magma supply from the double engine of ridge and hotspot, and an ocean pressing down on it that conveniently doubles as a measuring instrument. It is the laboratory mouse of volcanology, not because it is dangerous, but because it is clean. If eruption forecasting cannot be made to work here, the argument goes, it cannot be made to work anywhere. A method this clean deserved better luck than what came next. Because the years after 2015 quietly dismantled the assumption the whole calculation rests on. The threshold may well be repeatable. The 2015 success argues it is, and nothing since has disproven it. It is the other half of the arithmetic that betrayed them. The rate. The steady, rail-straight refill that made the 2015 forecast easy turned out to be the exception, not the rule. Since 2015, the magma supply to Axial has surged and stalled, sprinted and slumped, sometimes changing its pace by half within a single year. And when the rate keeps changing, the division keeps producing new dates. The line on the gauge holds still while the needle wanders toward it at a speed nobody can predict. Which is exactly how two scientists with the only confirmed forecasting win in volcanology found themselves, 10 years later, publicly crossing out one deadline and writing in another, and watching the volcano drift further off script with every passing month. That story, the story of the missed deadline, is coming in part 4. First, 2015, the night the method worked, the night a volcano erupted a mile underwater in complete darkness, and human beings watched it happen live. Part 3, the day we watched a volcano erupt live. Just before dawn on April 24th, 2015, the seafloor 300 miles off Oregon began to shake itself apart, and for the first time in human history, the instruments were already there, already on, and already connected to shore. Understand what eruptions at sea had always been before that moment. Rumours. A fishing crew reports discoloured water. A hydrophone thousands of miles away catches a low rumble that takes weeks to attribute. A research ship sails over a seamount a year later and finds the bathymetry changed, and scientists reconstruct the event like detectives at a cold crime scene. The 1998 eruption of Axial itself was pieced together that way, detected remotely, confirmed after the fact, its details forever fuzzy. Roughly 70% of Earth's volcanism happens on the ocean floor, and until 2015, essentially all of it had happened unwatched. This time was different, because by 2015, Axial had been wired. A cabled observatory, we will tour it properly later in this story, had gone live the previous year, streaming data from the summit to shore in real time. Seismometers that could feel a magnitude 1 tremor, bottom pressure recorders reading the height of the seafloor, hydrophones listening to the water column, all of it flowing continuously up a fibre optic line to Pacific City, Oregon, and out to any researcher with a login. So when the volcano finally moved, nobody had to wait for a ship, and it moved characteristically in the dead of night, the sequence ramping through the evening of April the 23rd and detonating in the early hours of the 24th. The earthquake catalogue simply exploded. The days before the eruption had been busy. The volcano had been muttering at rates around 500 to 1,000 small quakes a day, and the muttering was rising. Then, starting on April 23rd, the count went vertical. In roughly 24 hours, the seismometers logged about 8,000 earthquakes. 5 or 6 every minute, hour after hour, an entire year's seismicity for an ordinary volcano compressed into a single rotation of the Earth. The epicenters traced the walls of the caldera, and then streamed northward, mapping in real time the underground path of magma forcing its way out of the reservoir and into the northern rift zone. And beneath that swarm, the pressure recorders told the other half of the story in a single breathtaking curve. The floor was falling. As magma drained out of the reservoir, the caldera center dropped, not by inches, by 2.4 meters, nearly 8 feet of subsidence, the roof of the emptying chamber sagging downward, recorded centimetre by centimetre as it happened. Picture standing in a room where the floor quietly sinks by the height of a basketball hoop's backboard over a day and a half. The instruments rode it down and never stopped transmitting. Here is the detail that still gets cited in talks a decade later. The scientists were, in a sense, expecting it. Chadwick and Nuna had made their forecast public 7 months earlier. 2015 would be the year, because the inflation line was closing in on the 2011 threshold. When Chadwick's inbox began filling with automated alerts that morning, the feeling by his own account was less shock than recognition. The needle had touched the line, the valve had popped, the arithmetic had worked. In a discipline where, when will it erupt, had always been answered with decades-wide error bars, a volcano had just erupted on schedule. The hydrophones added a layer nobody expected: sound. As the eruption progressed, the underwater microphones picked up thousands of sharp, popping impulses rippling across the caldera, later analysed in a dedicated study of the 2015 eruption's acoustics, consistent with explosive bursts as seawater flashed to steam against fresh lava and as gas escaped the advancing flows. A mile down, under pressure that should smother almost any explosion, the eruption still found ways to detonate, and the observatory recorded every pop like a stethoscope taped to the patient's chest. Between the seismometers counting the cracking rock, the pressure sensors riding the collapsing floor, and the hydrophones cataloguing the explosions, the 2015 event became the first submarine eruption in history to be captured in full by an in-place observatory, start to finish, in real time, with nobody within 300 miles. What the eruption actually built, out there in the dark, took months to see. That summer, expeditions steamed out to survey the aftermath, sending robotic vehicles down through a mile of black water with lights and cameras. What they found was a lava field draped along about 7 kilometres, better than 4 miles, of the northern rift zone, and in places it was not a thin sheet of rock. One flow lobe stood so tall that the remotely operated vehicle Ropos had to climb 90 metres, 295 feet, the height of a 30-storey building, up its face to reach the top. Fresh, glassy black basalt stacked higher than most buildings in Portland that had not existed in March. The response expeditions that summer also delivered a quiet correction to the emergency itself. Mapping showed the new lava had come remarkably close to pieces of the observatory. Flows from the eruption's southern fissures had run near cabled infrastructure in the caldera's northeast, near enough that the margin between recorded the eruption and became part of the eruption was measured in hundreds of meters. The system had been designed with exactly this gamble in mind. To instrument an active volcano is to accept that the volcano gets a say in the experiment's duration. In 2015, the dice came up science. Every dive since has operated in the same knowledge. The next fissure opens where it pleases. And the strangest sight was not the rock. On top of the new flows, the cameras found the seafloor smoking with white. From cracks between the pillow lavas, clouds of pale, fluffy material came billowing out into the water. The crews call them snowblower vents, because that is exactly what they look like. Machines blasting snow across a black parking lot. It is not snow, and it is not ash. It is life. The flock is the product of microbial blooms, colonies of heat-loving microbes that live in the volcano's plumbing, feeding on the chemical energy of hydrothermal fluids, suddenly supercharged by a fresh eruption and multiplying so violently that their biomass comes fountaining out of the seafloor. Where a surface eruption sterilizes the landscape around it, an axial eruption sets the table. Within weeks, the newest rock on planet Earth was already a nursery, the first act of a colonization that would eventually recarpet the flows with microbial mat, and in time feed the tube worms and vent fields that make this seamount one of the most studied biological sites in the deep Pacific. Compare that experience to how the previous 2 eruptions reached human awareness, and you can feel how far the field had come. In January 1998, the first hint was acoustic. Earthquake tremor caught on distant hydrophone arrays originally built to track submarines, and it took ship expeditions to confirm that lava had actually reached the seafloor. In April 2011, the volcano erupted with battery-powered instruments sitting right on top of it, faithfully recording everything into onboard memory, where the data sat unread for months until a ship returned that summer and researchers discovered, after the fact, that they had missed the whole show. The forecast had even been broadly right, and nobody knew the eruption had happened until the evidence surfaced in July. 2015 was the first time the volcano moved and the scientists knew within hours. That difference, months versus hours, is entirely the cable, and it is why the fight over that cable, later in this story, matters so much. There is one more 2015 detail worth banking because it says everything about how robust this observatory is. The eruption happened around the instruments. Lava advanced through the caldera's northeast corner. Seawater flashed against fresh flows. The ground itself dropped 8 feet, and the network rode it out almost untouched, transmitting the entire time. The cable did not sever. The sensors did not drown in lava, though the flows came close enough to some infrastructure to make for nervous jokes on shore. The system was designed to survive the very event it was built to record, and in its first real test, it did. Every earthquake of the roughly 8,000, every centimetre of the 2.4-metre collapse, every acoustic pop, arrived on shore intact and time-stamped. When people ask why scientists trust the axial data so completely, why the entire forecast enterprise leans on these feeds without hedging, the answer is that this network has already been through an eruption and did not blink. That is the 2015 eruption's double legacy, and both halves bear directly on the deadline this whole story is about. The first half is proof of concept. Eruption forecasting, real forecasting with dates, is not impossible. It happened. Once, under ideal conditions, with a steady rate and a clean threshold, but it happened, and every argument about the 2026 deadline stands on that fact. The second half is calibration. Every number the current forecast leans on, the height of the threshold, the 2,200 quakes a day the volcano sustained in its final approach, the shape of the exponential climb toward failure, comes from the recording made that April. 2015 is the answer key. The entire current watch amounts to holding today's data up against that recording and asking, does this look like the last approach? And the uncomfortable answer, for nearly a year now, has been no. It does not look like the approach. It looks like the opposite. Which brings us to the deadline itself, the one that already failed and the one now burning down. Part 4. The missed deadline. The forecast that started all of this was issued in July of 2024, and by the method's own logic, it was a perfectly reasonable bet. The caldera floor was closing in on the 2015 trigger level. Magma was arriving at a brisk pace. The differential record was rising at roughly 15 centimeters a year, which works out to something like 25 centimeters a year at the caldera center, the second fastest sustained refill in the volcano's recorded history. Extend that line forward, and it crossed into the danger band within about a year and a half. Chadwick and Nuna did what their method told them to do. They said it out loud. Axial seamount will likely erupt by the end of 2025. That December, at the American Geophysical Union meeting, the largest gathering of Earth scientists in the world, the forecast went properly public, and the media found it. Then, the media found it again, and again. Through 2025, 3 separate waves of coverage rolled over this volcano, and we will come back to that circus later, because the gap between what the headline said and what the data said becomes its own part of this story. Out at the volcano, meanwhile, something less dramatic and more consequential was happening. The refill was easing. Not stopping, easing. The rate that had justified the forecast began slipping month by month from the pace of 2024. By late October of 2025, you can watch the confidence deflating in real time in the forecaster's own blog. The post from October 27th is titled, "With Painful Honesty, It's Starting to Feel Like Our Latest Eruption Forecast is Running Out of Time." The arithmetic in it is simple and merciless. The floor stood about 10 centimeters above the 2015 threshold, inside the band, with perhaps 20 centimeters of headroom left. But the rate of rise had sagged to around 10 centimeters a year in the differential record, down by a third from when the forecast was issued. Run the division again at the slower speed, and the crossing date slides out of 2025 entirely, landing somewhere in mid to late 2026. In that same post, Chadwick wrote the sentence that describes the entire post-2015 era of this project. Every time we try to estimate when the volcano might get there, the rate of inflation changes, making our forecast incorrect. Pause on the honesty of that October post, because it is rarer than it should be. Long-range forecasts fail in every field. Hurricane tracks shift, recessions arrive unannounced, but the standard institutional move is to let a failed prediction die quietly and hope nobody checks. Chadwick and Nuna run the opposite protocol. Every forecast, every revision, every miss goes onto a public blog, dated and archived, specifically so the record cannot be laundered later. The October post even walks through the exact arithmetic of its own failure. The differential rate at forecast time, roughly 15 centimeters a year. The rate by that October, roughly 10. The crossing date sliding from late 2025 into mid to late 2026 as a direct consequence. Anyone with division can audit them. In an information environment where the word forecast usually means an unfalsifiable vibe, this is the other thing Axial is testing, where the scientist can make hard predictions in public and survive being wrong. There was one more source of unease that fall, quieter than the arithmetic but harder to argue with. The earthquakes were wrong, not wrong in number alone, wrong in trend. Remember the answer key. In the final months before the 2015 eruption, Axial sustained roughly 2,200 small quakes a day, the sound of reservoir rock progressively cracking under load. In late 2025, with the floor already above the old trigger line, the volcano was producing a few hundred a day at best, often barely 100. There were flickers. A single day in late July of 2025 spiked above 2,000 events, and a few days that October cleared 1,000, and each flicker set off a fresh round of headlines. But the flickers never held. Each spike collapsed back into quiet within a day or two. Sustained acceleration, the actual signature of the last approach, never arrived. At a workshop that October, researchers working on Axial were polled on when it would erupt. Most said not this year. The people closest to the data had already stopped believing the deadline they were nominally still inside. The formal reckoning came on stage on December 16, 2025 at the AGU annual meeting, the same venue where the forecast had been unveiled a year earlier. Chadwick stood up and delivered the post-mortem himself, a talk that Science News summarized under a headline that captured the whole strange situation. An underwater volcano off Oregon didn't erupt in 2025 after all. Why not? Think about the position that talk put him in. A year before, the same room had heard the boldest eruption forecast in modern volcanology. Now the forecaster was back, with the volcano fatter than ever and conspicuously unexploded, explaining to his colleagues exactly which assumption had bent. Most scientific careers are built by never taking a swing that public. This project is built on taking the swing annually. December 31st, 2025. The year ends, the forecast dies with it, and the same team that made it did something you will almost never see in a scientist-worn news cycle. They published the miss, in public, under their own names, and took it apart. Axial Seamount did not erupt in 2025, the year-end post begins, and it does not reach for excuses. Their verdict on their own method is blunter than any critic's. Pattern recognition, watch the balloon, mark the old trigger line, extrapolate the refill, worked in 2015, only because the rate happened to be high and steady. As a long-range tool, it has proven in their word unreliable, for the simplest of reasons. The pattern can change, and it keeps changing. The rate is not a constant of nature. It is the moment-to-moment mood of a magma supply system nobody can see, 300 miles offshore and miles below the seafloor, and it has spent a decade refusing to hold still long enough for a straight line to mean anything. But the Post did not stop at the autopsy. It made a new bet, and this is where the story stops being about a missed date and becomes genuinely interesting. Because buried in the wreckage of the pattern method, the team believes they may have found something better, not a line on a gauge, but a physical signature of rock beginning to fail, a new kind of threshold, drawn not in centimetres of uplift, but in the relationship between the uplift and the earthquakes it generates. That method produces the deadline this whole story lives under, before the end of 2026, and it comes with a specific watchable trigger condition, a number that you, tonight, can check on a public website, and that currently sits about 5 times below where the theory says it needs to be. The forecasters also wrote down, in the same post, the thing skeptics would say for them. We realise, it reads, that we have repeatedly moved the goalposts forward in time, and that if we keep doing that, eventually we will be correct. There it is, the honest heart of this whole experiment. A team with volcanology's only confirmed forecasting win, keeping score against themselves in public on their second deadline in 2 years, with the volcano 4 months from the buzzer. Step back and look at the intervals themselves, because they frame how strange the current wait has become. 1998 to 2011, 13 years. 2011 to 2015, 4 years. 2015 to tonight, 11 years and 4 months, and counting. The current repose is already nearly 3 times the previous one, and closing in on the longest gap in the volcano's recorded history, all while the reservoir sits fuller than it has ever been measured. If the gap runs past 2027, Axial will have set a new instrumental era record for silence at precisely the moment it holds a record for load. Either the volcano's rhythm has fundamentally changed since 2015, or the past year's quiet is the long flat top of a curve that ends the way all the others ended, suddenly in the dark some night when the earthquake counter goes vertical. So what does the new method actually measure, and why did it produce 2026 instead of 2030? To answer that, you have to look at what the volcano has been doing this year, because 2026 at Axial has been, by every instrument on the mountain, the strangest year since the last eruption. The reservoir is fuller than it has ever been in the instrumental record, and the volcano has spent the year winding down. Part 5. Fully inflated, going quiet. 2026 arrived at axial seamount with every reason to be the year, and the volcano greeted it by doing something no one predicted. It took a vacation. The forecaster's blog post from March 17th carries a title you do not expect from a scientific monitoring update. Axial seamount seems to be taking a spring break. Behind the joke is a plot that genuinely puzzled the people who made it. The differential uplift record, the one built by comparing the pressure sensor at the caldera center against the sensor out on the eastern rim, showed the 6-month average rate of rise at 10.6 centimeters a year. Respectable. But the 3-month average, the recent behavior, had sagged to 5.7 centimeters a year. And if you looked at just the purple dots on the plot, the daily averages since mid-January, the line was nearly flat. The volcano that was supposed to be sprinting toward its threshold had, since roughly the start of the year, almost stopped climbing. It is worth pausing on what those plots actually are, because you can go look at them tonight. The Forecast blog publishes the raw material of every claim in this story. A noisy red curve that is the minute-by-minute depth difference between the two pressure stations, overlaid with coloured daily averages, orange dots reaching back 6 months, purple dots for the most recent 3, and fitted lines whose slopes are the rates everything hinges on. When this story quotes 10.6 centimeters a year or 4.5, those are the slopes of lines drawn through dots you can inspect yourself. There is no interpretive priesthood between you and the measurement. A retired teacher in Ohio can audit the state of a volcano a mile under the Pacific from a kitchen table, which is a sentence that would have read as science fiction to every volcanologist who ever chased this mountain by ship. The earthquakes told the same story in a different language. Through those same months, the count on the Public University of Washington feed ran below 100 earthquakes per day on most days, with occasional bursts of a few hundred. 100 a day may still sound like a lot, until you remember the calibration. This is a volcano that sustained 2,200 a day for months before its last eruption. In relative terms, the seismic engine was idling at less than 5% of its known pre-eruption output, while the reservoir stood at its highest fill level ever recorded. And here is the sentence from that March post that elevates this from a data curiosity to a genuine mystery. The researchers wrote, "In our previous post, we were anticipating seeing an increase in seismicity before the next eruption. Instead, the opposite is happening." Read that again. The team with the best data on any volcano on Earth, applying the lessons of the only successfully forecast eruption in history, expected the needle to move one way. It moved the other way. Whatever is governing this system right now, it is not the script. What causes a fully loaded volcano to ease off the gas? Chadwick's answer, in the same post, is the kind of honesty you get from a scientist who has been humbled by the same mountain for a decade. What is causing this? We don't know, but it must reflect how the supply of magma to the volcano is changing with time. That is the entire state of human knowledge on the question, from the man best positioned to answer it. The magma supply, the deep invisible pipeline delivering melt from the mantle into the shallow reservoir, is not a faucet fixed open. It surges, it slackens, and nothing in the data from above can currently explain its moods, because every instrument on the mountain watches the reservoir, and the pipeline that feeds the reservoir lies miles below the deepest thing anyone can measure. And remember the scale of the things being counted. When the feed logs 80 earthquakes in a day at axial, those are not events anyone would feel standing on the caldera floor if standing there were possible. Nearly all of them are magnitude 2 or smaller, the energy of a truck driving over a pothole, released 200 or 300 miles from the nearest land. Not one of them registers on any seismometer on shore. The entire seismic life of this volcano is invisible to every land-based network on Earth, and exists as data only because instruments happen to be sitting on the mountain itself. That is worth holding on to for 2 reasons. First, it means the quiet is real quiet, measured at point-blank range by sensors that can hear a magnitude 0. Nothing is being missed. Second, it previews the stakes of the funding fight coming later in this story. Unplug the cable, and this volcano does not go back to being poorly monitored. It goes back to being silent. Spring offered a head fake. By the May 9th update, the 3-month rate had perked back up to 8.3 centimeters a year. The spring break lull, the researchers noted, seemed short-lived, even as the 6-month average slipped from 10.6 down to 8.9. 2 curves, 2 directions, a system wobbling around a trend nobody could name yet. If you were looking for a reason to believe the countdown was back on, the May numbers gave you one. It did not survive the summer. Through the spring, there was one more current running under the science, and you could feel it between the lines of every post. The researchers were watching their volcano wobble, while Washington debated whether to keep the lights on. The May 9th update, with its ambiguous rebound, published 18 days before the descoping announcement that would threaten the entire observatory. Imagine extracting a clean scientific judgment from noisy data, while the instrument making the data has just been scheduled for dismantling. That was the working environment in which this year's most important volcano measurements were produced. Whatever else this story is, it is also a portrait of monitoring science as it actually exists. Not a serene machine, but a handful of people holding a long experiment together across funding cycles, administrations, and the indifference of the thing they study. The most recent full status report, July 23, 2026, the latest data in this story, settled the argument in the wrong direction. 6-month average, 6.5 centimetres a year. 3-month average, 4.5, both numbers down hard from May. The post's own title says it plainly. The rate of inflation is slowing again. Set the year's readings side by side and the shape is unmistakable. 10.6, 8.9, 6.5. The longer trend halving across 7 months, and the short-term rate, the volcano's current this quarter behaviour, down to 4.5 centimetres a year, which is not a sprint toward a threshold. It is a crawl. At 4.5 centimetres a year, covering the possible 20 remaining centimetres of headroom would take more than 4 years. The earthquakes, meanwhile, are still flatlined below 100 a day most days. Whatever the magma supply did in 2024, when it was driving the fastest sustained inflation since the 2015 run-up, it has spent 2026 progressively shutting itself down. So hold the full picture in your head, because it is genuinely strange. The reservoir, fuller than at any point in the instrumental record, 10 centimetres past the level that detonated it last time. The refill rate, decaying by the quarter. The seismicity, a whisper. The forecast, 4 months from expiring. The researchers' own framing, repeated in post after post this year, is a study in cognitive tension. The volcano is fully reinflated, and yet the next eruption is not imminent. Both true, neither comfortable. A loaded system that declines to fire is still loaded. Every month of quiet adds magma, however slowly, to a reservoir already past its historical breaking point. The slowdown does not diffuse the volcano. It only unschedules it. Play the possibilities forward, because from here the system has only 3 roads. Road 1, the magma supply surges back, the way it has surged before. 2024 proved the pipeline can still deliver at near-record pace, and a reservoir already past its trigger threshold gets shoved the final distance in months rather than years. Under that scenario, the current quiet reads, in hindsight, as the deep breath before the sprint, and the 2026 deadline survives on a technicality. Road 2, the decay continues, the rates grind towards zero, and the eruption drifts into 2028, 2029, beyond, a scenario with its own alarming subplot, because the machine watching the volcano has a funding expiration date, and on Road 2 the volcano may outlast its own observatory. Road 3 is the sneaky one. No resurgence at all, just the slow crawl of a critically loaded system inching to failure, because a volcano 10 centimetres past its historical breaking point does not strictly need new speed. It only needs 1 weak evening in the rock. On Road 3 there is no warning ramp, no months of accelerating swarms like 2015, just quiet, 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 and then 8,000 earthquakes. Nobody currently knows which road the volcano is on. That is not a rhetorical flourish. It is the literal stated position of the people with the best data on Earth. There is one more way to read these numbers, though, a way that says the calendar forecast was asking the wrong question all along. Not when does the floor reach a height, but when does the rock start to break. And by that reading, the thing to watch is not the centimetres at all. It is the relationship between the centimetres and the earthquakes, a single derived number with a threshold attached, and a value tonight that tells you exactly how far from the edge this volcano stands. That number is the current forecast. It is the reason the deadline says 2026, and it is the subject of the next part. Part 6. Counting Broken Rock. The new method was born from a simple confession. Height alone had failed. So in the wreckage of the 2025 forecast, Chadwick and Nooner went back through the archive and asked a different question. Forget when the volcano gets full. What did the rock itself do differently in the months before the last eruption? The raw materials were two data streams the observatory had been recording all along: the uplift from the pressure sensors and the earthquake count from the seismometers. Each had been watched separately for years. The insight was to divide one by the other, to ask for every centimetre the caldera floor rises, how many earthquakes does that centimetre cost? Think about what that ratio physically means. When the reservoir is young and the surrounding rock is relaxed, magma entering the chamber pushes the floor up almost politely. The crust flexes like the elastic waistband it essentially is. It stretches, it accommodates, and a centimetre of uplift generates only a modest crackle of tiny quakes. Engineers would say the deformation is elastic, reversible bending, no permanent harm. But as the pressure builds cycle after cycle, the rock runs out of stretch. More and more of the strain stops being absorbed by bending and starts being absorbed by breaking. Microfractures, slipping cracks, small faults grinding into new positions. The same centimetre of uplift now cost hundreds, then thousands of earthquakes. The ratio of quakes to uplift becomes a direct gauge of how close the roof of the reservoir is to structural failure. Low ratio, the rock is coping. High ratio, the rock is dying. You're no longer measuring how full the balloon is. You're listening to how loudly the balloon is creaking. If the idea sounds abstract, you have felt it in your hands. Take a paperclip and bend it once. It flexes and springs back, silent. Bend it further, past the point where the metal stops forgiving, and something changes in your fingers. The resistance goes grainy, the metal whitens at the crease, and each additional degree of bend costs visible, permanent damage. Materials scientists have known for a century that solids approaching failure announce it acoustically. Microcracks popping faster and faster per unit of strain, a phenomenon they monitor in bridges, mine roofs, and aircraft parts as acoustic emission. What Chadwick and Nooner are proposing is that a volcano's roof rock is no different, that the earthquakes per centimetre ratio is the acoustic emission signature of a 2-mile-thick slab of ocean crust, being bent past its elastic limit. The idea did not come from nowhere. It is the volcano-scale version of one of the oldest observations in fracture mechanics, applied for the first time to a system where both the bending and the popping are measured continuously at point-blank range for decades. Run that ratio over the 2015 archive and something remarkable appears. In the final 3 months before the April 24th eruption, the normalized rate climbed to roughly 10,000 earthquakes per centimetre of uplift, and stayed there. Not a spike, a plateau. For a quarter of a year, every centimetre of rise cost the volcano 10,000 fractures, sustained, right up until the morning the reservoir roof finally gave way and the whole system unzipped into the northern rift. The researchers' interpretation: that plateau may mark the onset of runaway inelastic deformation, the point where the rock's failure begins feeding on itself, where cracking begets cracking, and an eruption stops being a possibility and becomes a process already underway. If that is right, then 10,000 quakes per centimetre is not just a number. It is the sound a volcano makes when it starts to die, measured 3 months before anyone can see the wound. Now run the same ratio on today's data, and you understand the 2026 deadline. Since 2015, the normalized rate has been grinding upward, gradually with scattered single days flaring high, but never sustained at the 2015 plateau. The rock is creaking more per centimetre than it did 5 years ago, exactly as the theory predicts for a system approaching its limit. But it has not yet hit the sustained scream. The gap between here and the threshold can be expressed in a wonderfully concrete way. At the current rate of uplift, the researchers calculate, the volcano would need to be producing roughly 500 earthquakes per day for the normalized ratio to reach 10,000 per centimetre. 500 a day? That is the trigger condition of the current forecast, the tripwire strung across the data. Most days this summer, the count sits below 100. The distinction between a spike and a plateau matters enormously here, and it is where most of the scary headlines about this volcano go wrong. Axial has produced days that look, in isolation, like the end times. A single day in late July of 2025 cleared 2,000 earthquakes, comfortably inside the pre-2015 range, and a handful of October days broke 1,000. If you watched only the daily count, each of those days was a 5-alarm fire. But run the normalized ratio through them, and they deflate. Isolated bursts, likely the signature of a pulse of magma or fluid shouldering into the system, each one collapsing back to baseline within a day or two. The 2015 signal was not a burst. It was 3 months of sustained screaming, the ratio pinned at its ceiling week after week, the rock failing continuously rather than complaining occasionally. That is the discriminator the new method offers. It can tell an outburst from an approach, and by that discriminator, nothing in the last 11 years, not the 2000 quake day, not any of the flickers that launched 100 headlines, has qualified. Yet. So why does the forecast say before the end of 2026 and not some vague someday? Because the relationship between cumulative uplift and cumulative earthquakes at Axial is not linear, it is exponential. As total uplift accumulates, the earthquake cost of each additional centimetre multiplies. Chart the whole post-2015 record and the curve bends upward like compound interest. And extending that curve forward, the team expects the normalised rate to reach the 10,000 threshold before the end of this year. That extrapolation, the bending curve, not the straight line that failed them, is the entire mathematical content of the deadline this video is named for. It is, they would be the first to say, still a pattern bet. A more sophisticated pattern, one with a physical story attached about elastic rock giving way to breaking rock. But the volcano has eaten their patterns before. What would the crossing actually look like if it began tonight? Not a single dramatic day. The record is littered with those, and they mean little. The signature would build in the weekly rhythm, daily counts stepping up from under 100 to 200, 300, holding their gains instead of collapsing, the way a tide differs from a splash. The uplift rate would likely stir as well, the two curves rising together as fresh magma both lifts the floor and cracks the roof. Within a month of sustained climb, the normalised ratio would be visibly bending toward its ceiling on the forecaster's plots, and, if 2015 is the template, the system would then hold at the ceiling for weeks to months, screaming steadily, while the last strength drained out of the reservoir roof. That is the approach the method predicts. Not an ambush, but a crescendo with a long, audible final chord. The ambush scenario, quiet straight to detonation, Road 3 from earlier in this story, remains possible precisely because it has never been observed here, and it is the scenario that would break every method at once, and they say so. In the same year-end post that announced the new method, the team wrote the sentence their critics would have written for them. We realise that we have repeatedly moved the goalpost forward in time, and that if we keep doing that, eventually we will be correct, but without proving much in terms of the accuracy of our forecasts. There is something almost disorienting about reading that inside a forecast announcement. It is the scientific equivalent of a boxer announcing his own record honestly before the fight. 1 win, several losses, and here is exactly how you will know if I lose again. They even framed the stakes plainly. The big picture, they wrote, is that this is all an experiment to see how far the envelope of long-term eruption forecasting can be pushed at a volcano that is very active but poses no hazard to anyone. A perfect natural laboratory. Translation: we're allowed to be wrong here, in public, repeatedly, because being wrong here costs nothing. Remember that sentence when we get to the part of this story about the volcanoes where being wrong costs everything. But here is what makes the current moment at Axial richer than just a third swing of the bat. This time, they are not the only ones swinging. While the pattern recognition team was rebuilding its method in public, an entirely different approach was quietly plugged into the same data feed. A model built not on Axial's history but on the physics of how things break. A model with a genuine track record on landslides, on collapsing glaciers, on failing rock walls. It began generating its own predictions of this eruption in November of 2025, updating monthly, and its forecasts exist right now, written down, dated, and you cannot read them. Nobody can. That is not a failure of transparency. It is the point. Part 7. The Sealed Prediction. In the second week of November 2025, an experiment began at Axial Seamount that has no precedent in the history of volcanology, and its defining feature is an envelope nobody's allowed to open. The model belongs to 2 researchers on the other side of the world from the Volcano, Qinghua Lei at Uppsala University in Sweden and Didier Sornet at ETH Zurich in Switzerland. Sornet has spent decades studying a deceptively deep question. Is there a universal mathematical signature of failure? Not volcanic failure specifically, failure, period. the way a rock face microcracks before it collapses, the way a glacier's ice quakes accelerate before it calves, the way tremors quicken before a landslide lets go, the way material fatigue whispers before a structure fails. Across these systems, Sornet and colleagues have argued, catastrophic failure is often preceded by the same accelerating pattern, events cascading faster and faster in a mathematically recognizable run-up, as the system's remaining strength drains away. If you can fit that acceleration in real time, you can, in principle, solve for the moment it reaches infinity. The moment of failure. A date. Sornet in particular has spent a career hunting these signatures in places that share nothing but mathematics. Financial markets before crashes, material fatigue before rupture, seismicity before great earthquakes, pursuing the idea that complex systems near catastrophe develop a common grammar of acceleration, a measurable quickening as failure approaches. His critics have called the program overambitious. His admirers point to a long trail of documented tests. What matters for tonight is narrower and harder than any of the theory. The model in question is not a metaphor. It is a specific published mechanical failure framework, described in a paper posted publicly when the experiment began, with equations that ingest deformation and seismicity and output a time. Ley and Sornet built that model and tested it in retrospect against recorded disasters, landslides, rock bursts in mines, glacier collapses, and volcanoes, including past eruption data from Axial itself. In hindcasting, the model could recover the timing of failures it was shown, but hindcasting is aiming at a target after the arrow has landed. Every forecasting method looks brilliant in retrospect, because retrospect is where the answer key lives. The only honest test of a prediction machine is to point it at a failure that has not happened yet, write down its output, and wait. The mathematical heart of the approach is an idea called finite time singularity, and you do not need the equations to feel it. Plot the accelerating precursors of a failing system, the quickening ice quakes, the multiplying microcracks, and fit the curve that describes their acceleration. For a system genuinely running away toward failure, that curve does not climb forever at some steep slope. It bends toward vertical at a specific finite moment in time. The mathematics contains its own deadline. Solving for the moment the curve goes vertical is solving for the failure time, not as prophecy, but as a parameter of the fit, updated continuously as each new day of data sharpens or shifts the curve. Fed Axial's uplift and seismicity, the model is, in effect, asking every month, if this rock is on a runaway path, when does the runaway complete? The answer is a date with error bars, recomputed as the volcano speaks. That is exactly what began on the week of November the 12th, 2025. With Chadwick's enthusiastic cooperation, Ley and Sornet connected their model to the live data flowing from the observatory. The uplift, the seismicity, the same two streams everything else in this story runs on, and began generating true forward forecasts of Axial's next eruption. They update the forecast at least monthly, more often if the data warrants. Somewhere, right now, there is a current, dated, physics-based prediction of the eruption this entire video is about, and they will not tell you what it says, not Chadwick, not the press, no one. The forecast dates stay sealed until after the eruption happens, and only then will every forecast the model ever produced be published. All of them, hits and misses alike. So the world can judge the method against reality with no possibility of quiet revision. Think about why that rule exists, because it is aimed at the oldest failure mode in prophecy. A predictor who announces dates in public can shade them as the data shifts, retract the embarrassing ones, and trumpet the lucky ones. And after the fact, memory and motivated editing do the rest. Sealing the forecast kills every one of those outs. Whatever the model said in November, in December, in every month since, is on the record beyond reach. When Axial finally goes, the envelope opens, and the model is graded on its complete unedited transcript. It is the cleanest experimental design ever applied to eruption prediction, and it required a scientist secure enough to invite a rival method onto his own volcano, knowing the rival might succeed exactly where his own method keeps failing, and understand what the sealed envelope cost the people who sealed it. Every month that Axial makes headlines, Ley and Sornet hold a piece of information the entire story is starving for, an actual physics-based estimate of the date, and they say nothing, while less careful voices fill the vacuum with any day now. If their model is tracking beautifully, they get no credit until after the fact. If a journalist misrepresents the science, they cannot correct the record with their numbers, They have voluntarily accepted the one condition modern attention economies punish hardest: silence, held for the sake of a clean result. There is a name for the alternative, and every scientist in this field knows it. The tipster who mails 10 predictions and publicizes the one that lands. The sealed protocol is the exact inverse. All predictions on file, none selectable, everyone graded. Whatever the model turns out to be worth, the experimental design around it is already the gold standard, and other observatories are watching closely, because if this works at Axial, sealed real-time forecast trials could become the norm at volcanoes everywhere. Sit with the situation this creates, because there may be nothing else like it in science right now. Two forecasting philosophies are running head-to-head on the same mountain, on the same data, in real time. In one corner, pattern recognition, the almanac, Chadwick and Nuna's threshold logic, public, published, twice revised, currently promising an eruption by New Year's Eve. In the other, physics, the failure model, sealed, silent, updating monthly, its verdict unknowable until the volcano itself calls time on the contest. The volcano is the referee, and its decision is final and cannot be appealed. If the eruption comes and the envelope reveals the physics model tracked it while the pattern method missed again, volcanology will have witnessed its almanac to physics leap in a single event. If both miss, the field learns something darker, that even a perfect laboratory may not be enough. And there is one more possibility, the quietest one, that the referee simply declines to show up on anyone's schedule, and the contest runs on, month after sealed month, into years nobody budgeted for. Which raises a question this story has so far dodged. Everyone keeps saying the eruption is coming. This year, next year, eventually. The forecasters believe it. The sealed model presumably has dates, but 11 years have now passed since the last eruption, longer than the 4-year gap between 2011 and 2015, closing on the 13-year gap between 1998 and 2011. Is there anything in the volcano's deeper rhythm, anything beyond thresholds and ratios, that hints at when a mountain like this one likes to move? Strangely, yes, and it is written not in the rock, but in the calendar. Part 8. The Calendar. Wrinkle. Line up the 3 dates of Axial's instrumental era eruptions and an odd little pattern stares back at you. January 1998, April 2011, April 2015. 3 eruptions, and all 3 fall in the first third of the year, January through April. Not one summer eruption, not one autumn eruption. A sample size of 3 proves nothing on its own, and every researcher involved would say so before you finish the question. But the cluster has been noticed, discussed in the literature around this volcano, and it connects to something at Axial that is not folklore at all. Something measured, published, and frankly a little eerie. This volcano's earthquakes obey the tides. Volcanology has flirted with calendar patterns before and mostly been burned, which is why the researchers handle this one with tongs. Every few years someone correlates eruption catalogues with the seasons, with El Nino, with snow loading, with the wobble of the Earth's axis, and most of the correlations die under statistical scrutiny, victims of small samples and the human genius for finding faces in clouds. The honest ones survive in a specific niche, systems already at the brink where a genuinely tiny push gets recorded because there was nothing left to push against. Glacial volcanoes that stir as summer melt unloads their slopes, seasonal seismicity under reservoirs as water levels cycle. The principle is respectable even where individual claims are not. Loading modulates timing at the margin, never causation at the core. Axial's version of the question at least has a mechanism you can weigh. The ocean itself, the heaviest seasonal instrument on Earth, resting directly on the volcano's lid. The physics is real and beautifully simple. A mile of seawater sits on top of Axial's caldera, and that mile is not constant. Twice a day, the tide adds and removes a layer of ocean overhead, and with it thousands of pounds per square metre of pressure pressing down on the volcano's roof. When the tide is high, the extra weight clamps the system shut, squeezing the cracked rock of the reservoir roof together like a hand pressed flat on a creaking floorboard. When the tide is low, the hand lifts. The clamp eases, the stressed cracks are free to slip, and the seismometers hear it. Earthquake rates at Axial rise and fall with the tidal cycle, peaking when the water column above is lightest. Researchers analysing the cabled data, work associated with William Wilcox Group at the University of Washington, The same group whose earthquake counts anchor this whole story have documented the correlation. Tiny changes in load, a fraction of a percent of the total pressure on the system, are enough to modulate when a critically stressed volcano crackles. That is worth a shiver. The rock down there is so close to its limit that the moon's daily rearrangement of the ocean is audible in the earthquake catalogue. And if daily tides can gate the small quakes, the seasonal speculation almost writes itself. The ocean has slower rhythms too, annual cycles in currents, water mass, and loading. And some researchers have wondered aloud whether the January to April eruption cluster reflects a yearly minimum in the pressure holding the lid on, a season when the ocean leans on axial just slightly less, and a reservoir already at the red line finds its moment. It remains speculation with a sample of 3, unresolved and honestly labelled as such. But notice what it does to the timeline of tonight's story. The current forecast expires December 31st, 2026. The volcano's only known eruption season opens in January. If axial holds out just past the deadline, misses the forecast by weeks, and then erupts in the window where all 3 previous eruptions occurred, the pattern method will have failed by a technicality in the exact month history would have picked. The next January to April window opens 5 months from tonight. File that away. Put rough numbers on the clamp to see how delicate the balance really is. The full weight of the water column above axial exerts a pressure of roughly 140 atmospheres on the caldera floor. The tidal cycle swings that load by only a fraction of 1%, the equivalent of adding or removing a couple of meters of water from a column a mile deep. By any engineering intuition, a change that's small should be irrelevant to a rock mass under that much total load. And yet the earthquake catalogue responds to it, day after day, like clockwork. In fracture mechanics that is diagnostic, systems that respond seismically to loads that tinier systems sitting at criticality, so close to their failure threshold that the last percent of stress is being supplied by the environment's background hum. It is the same reason avalanche forecasters worry when a slope releases at the sound of a voice. The trigger is trivial. What the trivial trigger reveals about the state of the slope is not. None of this changes the physics of thresholds and ratios. The tides do not cause eruptions, any more than a starting gun causes a sprinter's speed. At most, the ocean decides the hour after the magma has decided the season. But it adds one more layer to the picture of a system balanced impossibly fine, and it makes the next question unavoidable. If this volcano is that sensitive, that loaded, that close, what happens to everything around it when it finally goes? What does an axial eruption do to the ocean above it, to the coast 300 miles east, to the one fault in this story that actually can kill people? It is time to deal directly with the fear that every headline about this volcano feeds on. Part 9. What it cannot do. Type this volcano's name into any social platform in a headline week, and you will find the same 2 fears over and over. It is going to send a tsunami at the west coast, and it is going to set off the big one, the Cascadia megathrust. Both fears sound reasonable. An erupting volcano, 300 miles off Oregon, in the same ocean as a fault capable of a magnitude 9. Tonight, let us do what the headlines will not and actually run the physics, because the answers are unusually clean, and they are both no. Start with the tsunami. Tsunamis need one thing above all: a sudden, large-scale displacement of the water column, a seafloor thrust upward by meters across hundreds of kilometers, or a mountainside collapsing into the sea. Axial's eruptions offer nothing of the kind. They are effusive, not explosive in any climate-shaking sense. Fluid basalt welling out of fissures and spreading along rift zones, under the crushing pressure of a mile of water that smothers violence like a fire blanket. The 2015 eruption, the largest event at this volcano in the instrumental era, moved the caldera floor down 2.4 meters, slowly, over a day and a half, across a bowl a few miles wide. The sea surface directly above registered nothing a passing ship could have felt. Compare the one submarine eruption in living memory that did produce a devastating wave, Hunga Tonga in 2022, a shallow water explosive volcano whose summit sat close enough to the surface for the blast to punch directly into the atmosphere and the water column at once. Axial is the anti-Tonga, too deep, too gentle, and the wrong style of volcano entirely. The United States Geological Survey states it flatly. Axial poses no threat to people or ocean travel. No wave, not a small one, none. The contrast with earthquake tsunamis makes the physics vivid. When a subduction zone like Cascadia ruptures, it jerks a strip of seafloor the size of a state upward by meters in seconds. The ocean above has no time to flow out of the way. The entire displaced volume becomes a wave, and the wave crosses oceans. Axial's 2015 collapse moved a bowl a few miles wide downward by 8 feet, over a day and a half. At that speed, the ocean does not lurch. It seeps, flowing gently sideways to fill the slowly forming depression, dissipating the entire displacement as imperceptible currents. Same vertical scale, wildly different clock, and the clock is everything. Tsunamis are born from suddenness, and this volcano does nothing suddenly except crack rock too small to matter. Even the theoretical worst cases published for submarine volcanic flank collapses involve edifices shedding entire mountainsides at once. A failure mode Axial's low, gently sloped shield profile does not offer. Now Cascadia, and here the geography does the heavy lifting. Look at where these two systems actually live. The Cascadia subduction zone runs along the coast, where the Juan de Fuca plate dives beneath North America, a compression machine, 2 plates grinding together, storing centuries of strain. Axial sits 300 miles farther west on the Juan de Fuca ridge, the opposite edge of the same small plate, where the seafloor is being pulled apart and brand new crust is born. They are different machines doing opposite jobs, connected only in the sense that every piece of a planet is connected to every other piece. For an axial eruption to trigger the megathrust, its stress changes would have to reach the locked zone at meaningful strength. Static stress transfer decays brutally with distance, by the inverse cube, and across 300 miles the nudge from a seamount quietly draining its magma reservoir arrives at Cascadia thousands of times weaker than the stress changes the fault absorbs, without complaint, from ordinary ocean tides every single day. As for shaking, the largest earthquakes Axial produces, even mid-eruption, are around magnitude 2. Energy releases millions of times too small to reach the megathrust as anything but a whisper beneath the noise floor. 8,000 of them in a day in 2015 did precisely nothing to the coast. The volcano has erupted 3 times in 28 years with Cascadia locked and loaded the entire time. The megathrust has not so much as flinched. It is worth saying what makes this so unusual in the world of volcano coverage, and on this channel. When we covered the volcano erupting under the Pacific that almost no one is watching, back on August 14th, the unease was justified. That seamount sits in a populated island arc, shallow enough to matter with essentially no instruments on it. Axial as that story turned inside out. This is a volcano with more instruments than any on Earth, and no victims available even in principle. When it erupts, the entire human toll will be some overworked graduate students, several very excited scientists, and a few billion microbes launched into the greatest bloom of their careers. That is the complete casualty list. The fear is imported, borrowed from land volcanoes, where the same word, eruption, means ash and lahars and buried towns. Out here the word means the seafloor quietly paving itself in the dark. And that safety is not a footnote to this story. It is the load-bearing fact of the whole experiment. Axial is the one volcano where scientists can afford to publish a hard deadline, blow it, revise it, and blow it again, because no evacuation hangs on their arithmetic, no economy empties on their say-so, no one dies of their false alarm. Every failed forecast here is free tuition. The nightmare scenario is not this volcano surprising anyone. The nightmare is needing this skill, dated, confident, 7 months out eruption forecasting, at a volcano where the stakes are the opposite of 0 before the tuition is paid. Hold that thought. But first, none of this works. None of it exists without the machine. The cables, the 140 instruments, the observatory that nearly went dark this summer while the whole world was watching the volcano instead of the budget. That fight is next. Part 10. The Machine That Watches. Everything in this story, the deadline, the sealed forecast, the ratio, the entire premise that a volcano a mile underwater can be watched at all, runs through one physical object, a loop of fiber optic cable lying on the floor of the Pacific Ocean, and it is time you met it properly. It is called the Regional Cabled Array, and it is one of the most ambitious scientific instruments the United States has ever built. Roughly 660 miles of submarine cable run out from a shore station at Pacific City, Oregon, across the continental shelf, down the slope and out over the abyssal plain, carrying not data alone but power, real electricity to the bottom of the sea. Off that backbone hang the instruments, more than 140 of them across the array, planted on the seafloor and strung up through the water column on moorings, seismometers, bottom pressure recorders, tilt meters, hydrophones, cameras aimed at hydrothermal vents, chemical sensors tasting the water. The whole assembly cost on the order of $386 million to build, and it is operated by the University of Washington as part of the National Science Foundation's Ocean Observatories Initiative, the OOI. One branch of the backbone climbs the flanks of axial seamount and wires the summit caldera itself. That branch is why this volcano is the best monitored piece of volcanic real estate on planet Earth. Better instrumented than Vesuvius, better than Yellowstone, better than any mountain standing over any city, because no land volcano streams this density of measurement from this close to its magma. Consider what it took to build. The array went live in 2014 after years of design, cable-laying ships, and remotely operated vehicles placing instruments by robotic arm on terrain no human has ever touched. The engineering brief reads like a dare. Deliver utility-grade power and broadband to sites under a mile or more of corrosive salt water. Design junction boxes that ROVs can plug and unplug on the seafloor like sockets in a wall. Build sensors that hold calibration for years while being crushed, frozen, and occasionally menaced by fresh lava. At Axial's summit, the wired inventory includes seismometers spaced around the caldera to triangulate every crack, the bottom pressure and tilt instruments whose plots anchor this entire story, hydrophones, chemical sensors sipping the vent fluids, and a high-definition camera that stares at a hydrothermal chimney and streams video of a world of tube worms and shimmering 300-degree water to anyone on the internet. The data is public. All of it, in real time. The earthquake counts this video keeps citing are not privileged access. They are a website, updated continuously, run by William Wilcock and Mochuan Zhang at the University of Washington, sitting open to any citizen of Earth with a browser. Set the price in context too, because $386 million sounds enormous until you shop around. It is roughly the cost of a single F-35 squadron's worth of spare parts, a fraction of one aircraft carrier's annual operating budget, less than some single Hollywood productions. For that one-time price, the United States acquired something no other nation possesses, a permanent live nervous system wired into the seafloor of an entire tectonic plate, the volcano, the spreading ridge, and the approaches to the Cascadia margin, all reporting continuously. Other countries run cabled ocean observatories. Japan's earthquake monitoring networks above their subduction zones, Canada's Neptune array on the northern half of this same plate, but nothing anywhere wires a whole active volcano at this density. It is a genuinely singular instrument, and it exists because for one funding window in the 2000s, the United States decided that the bottom of the ocean was worth watching properly. The array is the difference between knowing and guessing. We have seen that difference play out 3 times now in this story. 1998. Months of ships and inference to confirm an eruption had even happened. 2011. The eruption recorded perfectly by instruments nobody could hear, discovered 3 months late like a letter found behind a couch. 2015. 8,000 earthquakes streamed to shore as they happened, scientists watching a volcano erupt from their desks. Same volcano, same scientists. The only variable was the wire. Live on that wire, incidentally, is one of the internet's most quietly astonishing destinations. The camera at the Ashes hydrothermal field points at a chimney the researchers named Mushroom and streams it, a mineral tower wrapped in mats of bacteria, crawling with scale worms, wreathed in shimmering fluid hot enough to melt lead, sitting in blackness a mile down on an active volcano's summit. People have watched sunrise time-lapses of Yellowstone geysers for a century. This is the deep ocean equivalent, running continuously, and almost nobody knows it exists. It matters to tonight's story for one reason beyond wonder. That camera, those vents, and every tube worm in frame sit on the caldera floor that drops 8 feet when this volcano goes. The 2015 lava flows stopped short of the main instrument clusters. The next eruption gets its own vote. Part of what the observatory is watching for in the end is its own possible destruction, and the engineering answer to that risk was not to move the instruments to safety, but to accept that a front row seat sometimes ends up inside the show. which is why what happened this June should have gotten far more attention than it did. On May 21st, 2026, the National Science Foundation announced what it called a descoping of the Ocean Observatory's initiative, a bureaucratic word for shutting most of it down. Ocean monitoring arrays across the global network would be discontinued. On June 1st, the New York Times put the plan on its pages under a headline with no soft edges: Trump administration to dismantle ocean monitoring system. The reporting spread through the Seattle Times, Oregon Public Broadcasting, regional radio, and for anyone following the Axial story, the timing read like dark satire. The most closely watched volcano on Earth, fully inflated, inside a public forecast window, and the plan on the table was to start unplugging the ocean. Inside the research community, the first days after the announcement had the texture of a bereavement. Scientists interviewed by Pacific Northwest outlets described being stunned. Decades-long careers built on data streams that were now scheduled to simply stop. The word that kept surfacing was continuity. An ocean record is not like a telescope you can switch off and resume. The value of a 20-year temperature or chemistry curve lives in its unbrokenness, and a gap of even 2 years cannot be backfilled by any future budget, because the ocean of 2026 will never exist again to be measured. For the Axial program specifically, the threat was close to existential. The volcano was inside a forecast window, fully inflated, and the instruments watching for the climactic data point of a 20-year experiment were on the chopping block before the experiment could end. The reaction was immediate, loud, and, in a political era not known for it, bipartisan. Oregon Senator Jeff Merkley led the fight in Congress, and lawmakers from coastal states piled on with a blunt argument. This system watches earthquake country, the same cable network that monitors axial threads through the neighborhood of the Cascadia subduction zone. The fault this channel has covered again and again, the one that actually can level coastal cities, and observatory data feeds directly into understanding it, with obvious implications for earthquake and tsunami readiness. Oregon lawmakers called the removal a direct threat to the coast. Scientists went public in numbers, describing decades of continuous climate and ocean records that would simply stop. For 2 weeks in June, the fate of the wire was a live political fight. Stories running on the same days the volcano's own uplift plots were quietly flattening. And then, on June 18th, it reversed. The NSF posted an update announcing the UOI would not be dismantled after all. CNN's headline credited furious bipartisan backlash. The relief in the research community was real, and strictly partial. Because the surviving plan is not restoration. Under the descoping that stands, the OI's other ocean arrays are still being discontinued. The regional cabled array, Axial's array, was singled out for survival, but with a horizon attached. Funding to operate it runs through September 2028. After that, in the words of everyone involved, it is unclear what happens, and the erosion did not stop with the arrays. 4 days after the reversal, on June 22nd, Science reported that core NSF research programs were being quietly slashed to fund other initiatives, cuts that directly hit the program financing the axial forecasting research itself. The machine survived. The mission is bleeding, so write the timeline of this summer down in one place, because the juxtaposition is the story. May 21st. The government moves to dismantle the observatory. June 1st, the plan hits the front page. Mid-June, Congress fights. June 18th, reversal, with a 2028 expiration date attached. July 23rd, the volcano's latest data shows inflation slowing again, the eruption drifting later even as the observatory's guaranteed lifetime shortens. 2 countdowns running in opposite directions, and that collision produces the strangest sentence this channel has written in a long time. The best monitored volcano on Earth now has a real chance of erupting after its monitoring ends. Part 11. 2 clocks. Let us take that collision seriously and actually race the clocks, because the arithmetic is uncomfortable. Clock 1, the volcano. The standing forecast says before the end of 2026, 4 months and change from tonight. But that forecast requires the earthquake rate to climb roughly 5-fold to its tripwire, and the volcano has spent all year moving the other way. The honest error bars by the researcher's own record of revisions run years, not months. If the slowdown continues, the crossing arithmetic at current rates stretches past 2028 without strain. Chadwick himself, describing the pattern method's decade of misses, has effectively conceded the point. The volcano sets its own schedule, and the schedule has been running late for 10 years. Clock 2, the machine. September 2028 is the horizon, 25 months after tonight. Beyond it, nothing is promised. Perhaps funding is renewed and the array runs for decades. The scientific case is overwhelming and the infrastructure is already paid for. Perhaps it is not renewed, and the most instrumented volcano in history goes dark with its reservoir still loaded. Federal science budgets are being cut in real time. The June reversal saved this array from immediate dismantling, not from the next budget cycle. Nobody watching honestly can call Clock 2 safe. Now, overlay them. If the eruption comes this fall, the forecast's last stand, everything aligns. The array records its second eruption in full, the sealed envelope opens, both methods get graded, and volcanology banks the richest eruption dataset ever collected, with years of observatory life left to study the aftermath. If the eruption comes in 2027 or early 2028, much the same, with less margin. But slide the eruption past September 2028, well within the honest error bars, and the whole experiment inverts into farce. 2 decades of build-up meticulously recorded. The refill documented centimetre by centimetre, from the 2015 collapse through the record inflation of this year. Every precondition captured in exquisite detail, right up to the moment the money ran out, and then the payoff, the eruption itself, the entire point of the enterprise, happening unrecorded in a dark ocean, reconstructed afterward by some future expedition, measuring how much the bathymetry changed. The 2011 fiasco again, except worse. That time the instruments recorded everything, and nobody was listening for 3 months. This time there would be no instruments at all. Weigh, also, what renewal would actually cost against what abandonment forfeits. The construction money, the hard part, the ships and cable and robotics, is spent. It is sunk cost in the most literal sense in the English language. What expires in September 2028 is operations funding, the shore station, the data pipeline, the maintenance cruises that swap failed sensors. Walking away does not recover the investment. It strands it. Hundreds of millions of dollars of functioning infrastructure left powered down on the seafloor, while the specific scientific question it was built to answer sits one eruption from resolution. There may be no cleaner case study anywhere in federal science of a machine whose remaining mission is short, defined, and already paid for in everything but electricity, and you would not even know the eruption had happened. That is the detail worth sitting with. When Axial erupts, no satellite sees it, no coastal seismometer feels it. The tsunami buoys register nothing, because there is nothing to register. Without the array, the most active volcano in the United States erupts with literally zero human awareness. The news arriving months or years later, when a research cruise notices the seafloor is shaped differently. We covered a volcano in exactly that condition 6 days ago. The seamount in the western Pacific that had been erupting on and off, with no instruments within 1,000 miles. Its activity deduced from discoloured water and distant hydrophones. The lesson of that video was that the ocean hides its volcanoes by default, and that watching one requires deliberate, expensive, sustained choice. Axial is the one place on Earth where that choice was made fully, where humanity built the machine, paid the money, and kept the light on for 2 decades. The question this summer put on the table is whether the one lit window in the world's darkest wilderness gets shuttered 25 months from now, with the tenant visibly awake inside. What would watching Axial even look like after the cable? The fallback is the world this story began in. Battery instruments dropped by ship, recording into memory, recovered a year later. The trail camera era. Annual expeditions could remeasure the benchmarks the way Nuna's campaigns once did, reconstructing the inflation curve in yearly snapshots instead of 20-second samples. It would not be nothing. It would also miss everything that matters. The tripwire of the current forecast is a sustained daily earthquake rate, a quantity that simply does not exist in a dataset visited once a year. The sealed physics model consumes real-time feeds, starve it and the experiment ends mid-sentence, and the eruption itself, whenever it comes, compresses its entire diagnostic story, the swarm, the migration, the collapse, into about 48 hours. A snapshot program does not record a 48-hour story. It finds the aftermath, Like the 2011 letter behind the couch, and the golden age of watching this volcano closes exactly where it opened, with scientists inferring from changed rock what they once would have watched live. The 2011 episode, read closely, previews exactly what a post-cable eruption costs, because even that recorded eruption lost things that never came back. The instruments caught the earthquakes and the deflation, but by the time anyone knew and a ship could respond, months had passed, and eruptions at sea are perishable crime scenes. The snowblow events that so astonished the 2015 response teams are transient. The microbial blooms peak and fade within months. The chemistry of fresh lava interacting with seawater, the short-lived venting, the immediate biological succession, all of it has a shelf life measured in weeks. In 2015, with same-day awareness, expeditions reached the site in time to catch the aftermath alive. The resulting studies filled journals. In 2011, the perishable science simply rotted unobserved. A post-2028 eruption would be 2011 again at best, and without the battery instruments, not even that. The difference between those futures is a budget line that expires in 25 months. There is a broader ledger here too. The regional cabled array does not exist for axial alone. Its sensors ride the Cascadia margin, sampling the ocean above the fault that will someday write the worst day in Pacific Northwest history. Its moorings record the ocean's temperature, oxygen and chemistry in continuous decades-long curves that climate science cannot get any other way. Records whose value comes precisely from being unbroken, and which a 2-year shutdown would sever permanently. When the June fight was on, that was the argument that moved Congress. Not the volcano, but the coast. It is worth being honest that the volcano rode to safety on Cascadia's coattails. Fitting, in a way. The gentle volcano that cannot hurt anyone was saved by its proximity to the fault that can hurt everyone, and the machine that watches both now runs on a lease that expires before either is expected to move. Part 12. The Hype Machine. While the scientists were watching the volcano, this channel was watching something else, the coverage. And the coverage of axial seamount over the past 2 years is a case study in how science news actually breaks. Worth a few minutes of this story because it explains why you should trust the numbers in this video and almost nothing you have seen in a headline about this volcano. Here is the pattern, documented with some bemusement by Chadwick himself on the Forecast blog. After the 2025 forecast went public at the December 2024 AGU meeting, a first wave of media coverage rolled through in January. Reasonable enough, the forecast was genuine news. It ran its course and faded. Then in May of 2025, a second wave erupted. NBC, NPR, USA Today, the LA Times, triggered as far as anyone can tell by nothing. In Chadwick's own italics, even though nothing had changed. No new data, no new forecasts, no new activity. One outlet rediscovered the story and the pack followed, each citing the others, a feedback loop with no volcano in it. Then, in August of 2025, a third wave, ABC News, local Portland television, People magazine of all outlets, again with, in the forecaster's words, nothing changed. 3 full media cycles, 1 stationary fact. By the third wave, headlines had escalated to could erupt any day now, a phrase no scientist on the project ever said, describing a volcano whose data feed was, at that exact moment, whispering along at 100 quakes a day, with its inflation rate sagging. What sparked Wave 3? The forecaster's best guess is instructive, possibly a single blog post noting that the volcano had produced over 2,000 earthquakes in one day at the end of July. One day. We spent part 6 of this story learning exactly what such a day means. An isolated burst, a pulse in the plumbing, collapsing back to baseline within hours, explicitly not the sustained signature of an approach. But a 2,000 quake day does not arrive in a newsroom with its normalized ratio attached. It arrives as a big number next to the word volcano, and the escalation machinery does the rest. Number becomes spike, spike becomes surge, surge becomes could blow any day, and by the time the story reaches a celebrity magazine audience, a research seamount incapable of harming a single human being is wearing the costume of a coiled disaster. Meanwhile, the actual data feed that generated the number sat publicly available the entire time, showing the burst dying out, 1 click away from every newsroom that never clicked. The forecasters watched their own story mutate with a mixture of amusement and alarm, and Chadwick drew the distinction that matters. The reporters who called, asked questions and checked facts wrote accurate stories. The ones who wrote from other reporting produced the any-day genre. The difference between journalism and aggregation, measured on a single volcano. His summary of the accurate version was almost poignant in its modesty. Nothing looks imminent, and it poses no threat to humans anyway. Try fitting that in a headline font. There is a wave 4 warning embedded in all this, and you can set your watch by it. Sometime in the next 4 months, as the December 31st deadline enters its final weeks, the cycle will spin up again. Count on headlines pairing the words deadline and volcano with imagery of destruction the physics cannot deliver. And when the deadline passes, whichever way it goes, the machinery runs once more. Either eruption confirmed off Oregon coast atop a story that never mentions the decade of method building that cooled it, or scientist volcano prediction fails again atop a story that never mentions why failing in public was the entire design. The one version you are unlikely to encounter is the one you now have, a running experiment, honestly scored, at the only volcano on Earth where the score can be kept clean. Chadwick has turned the experience into something like a public service routine. When he gave a talk to a geoscience society in Bend, Oregon this May, he opened it, before the volcano data, before the forecasts, with what he called the good, the bad, and the ugly of media reporting on Axial. Think about that ordering. The scientist with the most interesting active volcano dataset on Earth now finds it necessary to begin public talks by triaging the coverage of his own work, separating the checked from the recycled from the invented, because he knows the room arrives preloaded with headlines. It is a small window into a real cost of the hype cycle that never appears in any correction box. The hours scientists spend unteaching what the coverage taught at the expense of the far stranger true story they could be telling instead. But there is a deeper irony in the hype, and it cuts against the usual complaint. The standard media failure with volcanoes is manufacturing fear about nothing. Here, the media manufactured fear about the wrong thing while the genuinely riveting story sat unreported. Underwater volcano could erupt any day is false and boring. The truth. Scientists have put a public expiration date on an eruption for the second time. A sealed rival forecast is running in real time. The volcano has drifted off its own script while critically loaded, and the machine watching it all nearly got unplugged mid-experiment is accurate and better. The hype machine took the one volcano story with a genuine scientific thriller inside it and flattened it into the same disaster bait template it uses for every mountain. If you came to this video from one of those headlines, the volcano was never going to hurt you. What is actually at stake out there is not your coastline. It is whether the human species is about to learn how to schedule an eruption. And that story, the real one, has an ending nobody knows yet. Part 13. What the next eruption decides. Strip away the deadline drama, the budget fight, the sealed envelope, and ask the plain question underneath this entire story. Why does it matter whether anyone can forecast an eruption at a harmless seamount 300 miles out to sea? The answer lives on land, and it is measured in cities. Run the inventory of what sits under volcanoes on this planet. Naples, pressed against the slopes of Vesuvius and cradling the restless caldera to its west, with hundreds of thousands of people inside evacuation zones that would need days to empty. A crisis this channel walked through earlier this month. Seattle and Tacoma, in the lahar shadow of Rainier, where children in valley towns practice walking uphill because the mud from a collapsing volcano could arrive faster than traffic can move. Mexico City, 60 miles from Popocatépetl. Tokyo, in ash range of Fuji. Jakarta, Manila, Quito, Kagoshima. Tens of millions of people on every continent with a coastline on the Ring of Fire, living on the promise that when their mountain finally moves, somebody will call it early enough to matter. This channel has spent the month inside that promise's fine print. We watched a caldera in Europe whose evacuation plan assumes 72 hours of clean warning for 1 million people on narrow roads. We watched a Cascade volcano whose lahar detection system, by its own designer's description, detects but does not predict. It buys the valley towns minutes, not months. Again and again, the pattern is the same. The hazard maps are excellent, the response plans exist, and the single missing input, the one number every plan is built around and none can generate, is time. How much warning, at what confidence, how far out. That number is the entire deliverable of the science being tested off Oregon. And here is the uncomfortable truth behind that promise. The current state of the art is mostly short-fuse warning, not long-range forecast. Modern volcano observatories are genuinely good at recognizing the final act, the accelerating swarms, the deformation, the gas changes that mean an eruption is likely within days to weeks. That skill saves lives, and it has. But days to weeks is a brutal window in which to move a metropolis. The evacuation plan for the Naples caldera alone runs 72 hours just for the stage departure, on the assumption that the call comes clean and everyone cooperates. And the history of volcanic crises is a history of calls that did not come clean. False alarms that emptied cities for nothing and poisoned the public's trust for the next alarm. Real warnings issued into that poisoned trust and ignored. The difference between a forecast measured in months and a warning measured in days is the difference between an orderly relocation and a panicked weekend, between an economy that winds down gently and one that shatters. Months of confident lead time at a dangerous volcano is, without exaggeration, one of the most valuable pieces of information civilization does not yet know how to produce. That is what Axial is for, not the volcano itself, the skill. Axial is where the skill is being invented because Axial is the only place on Earth where every ingredient of the problem exists, without the ingredient that makes practicing on real cities impossible: consequences. The volcano erupts often, so hypotheses get graded within careers rather than centuries. The instruments are the best ever assembled, so no failure can hide in missing data. And nobody can die, so a forecaster can post a date, miss it, revise it, and miss again, in public, at a cost of exactly nothing but reputation. Every one of those misses, and this story has now walked through a decade of them, is tuition paid at the one school where tuition is free. The 2015 success proved the concept is not fantasy. The failures since have been mapping, with precision, exactly where the concept breaks. The pattern holds until the pattern changes. The rate is the treacherous variable. The threshold may be real, but the road to it is not a schedule. That map of failure modes, bought at zero human cost, is the most transferable product this seamount makes. Because the transfer is the dream, and it is not a vague one. If the normalized seismicity threshold works, if sustained earthquakes per centimeter really is the sound of reservoir roof rock entering runaway failure, that ratio is not an axial-specific trick. Deformation and seismicity are the two quantities every serious observatory on Earth already measures. The ratio between them can be computed at Vesuvius, at Rainier, at Popocatépetl tonight from existing feeds. What no land observatory has is the calibration, the known value of the ratio at the moment of eruption, measured through a complete cycle. Because no land volcano offers cycles fast enough or data clean enough to build one. Axial can hand over a calibrated instrument instead of a hypothesis. The same logic runs for the sealed physics model, a mechanical failure framework that graduates from Axial with a verified real-time forecast to its name, becomes a candidate for every volcano observatory on Earth, and one that fails here, under perfect conditions, warns the field off a blind alley before any city bets on it. Either grade is valuable, only silence, an unwatched eruption, an unfinished experiment, teaches nothing. If the stakes still feel abstract, history offers two nights that make them concrete. In November of 1985, Nevado del Ruiz in Colombia erupted beneath its ice cap after a year of visible unrest. Scientists had mapped the mudflow hazard. The maps existed. The town of Armero sat squarely inside the red zone. What did not exist was a forecast confident enough, early enough, and trusted enough to force the hard decision. And on the night the lahars came down the river valleys, more than 20,000 people died in a town that had hours of warning and no conviction behind it. 6 years later, the counterexample, Pinatubo, in the Philippines, 1991. Scientists reading the mountain's acceleration called the eruption days ahead. Authorities moved tens of thousands of people, and one of the largest eruptions of the 20th century became a story of catastrophe largely dodged. The margin between those two outcomes was not instrumentation alone. It was forecast confidence, delivered in time to act, believed by the people who had to act on it. Days of confident warning saved Pinatubo's evacuees. Months would have saved Armero calmly, without the last-night gamble at all. Months is exactly the product Axial is trying to learn how to manufacture. There is a precedent for all of this, and it is worth naming because it reframes the missed deadlines entirely. Weather forecasting spent its first century as a public joke. The almanac era, the folklore era, forecasts wrong so routinely that the profession was a stock comedy figure. It became the quiet triumph it is today through exactly the machinery now assembling around this volcano. Dense permanent instrument networks, physics-based models run against real-time data, and, crucially, an unbroken culture of verification, every forecast graded against outcome, every miss archived and mined. Nobody remembers the individual blown forecasts of 1950. Everybody lives inside the skill they purchased. Volcanology has never had a laboratory where that loop could run. Forecast, outcome, grade, revise. Because volcanoes erupt too rarely and observatories cannot afford to be wrong in public. Axial is the first place in history where the loop runs freely. The blown 2025 deadline is not an embarrassment to this program. It is the program, one full turn of the crank that every mature forecasting science had to turn 10,000 times. There is one more thing the next eruption decides, quieter than the forecasting verdicts, but arguably as important: whether the magma supply question ever gets answered. The deepest unknown in this whole story, the reason every deadline has died, is the pipeline below the reservoir, the unmeasured connection between the mantle's melt production and the shallow chamber the instruments can see. Why did it sprint before 2015 and stagger ever since? Why did it surge in 2024 and fade through 2026? Every cycle the observatory records, every full sequence of refill, slowdown, resurgence, and eruption, is one more constraint on that hidden plumbing, one more data point on how a mid-ocean magma system actually breathes. The 2015 cycle gave science its first complete continuously recorded refill. The current cycle, precisely because it has been so erratic, may be the more valuable of the two, a natural experiment in supply variability, running under full instrumentation. Provided, as always, that the instruments are on when the cycle closes. So when the next eruption comes, this year on schedule, or years late in defiance of every method, the moment the caldera floor drops, 3 verdicts arrive at once. The pattern method learns whether its threshold band was ever real. The sealed envelope opens, and the physics model learns its grade in front of the world. And volcanology learns whether its almanac era is ending, whether the 20-year bet that a wired volcano could teach us to schedule eruptions pays out, or whether the honest answer is that even the cleanest volcano on Earth keeps its own counsel. Every one of those verdicts requires the same thing, that the machine is still on when the moment comes, which returns us one last time to tonight, to a dark caldera, a slowing needle, and the numbers that will tell you before anyone announces it that the moment is arriving. Part 14. The Watch. So here is where everything stands tonight. August 20th, 2026, 300 miles west of Oregon and a mile down. The caldera floor stands higher than it has ever stood in the instrumental record, roughly 10 centimeters above the level that detonated the volcano in 2015, inside the band where its last 2 eruptions began, with perhaps 20 centimeters of theoretical headroom above it. The refill that drove it there has decayed all year, 10.6 centimeters per year, then 8.9, then 6.5 on the 6-month average, 4.5 on the most recent quarter. The earthquake rate idles below 100 a day, 5% of the pace that preceded the last eruption, a factor of 5 below the tripwire the current forecast needs it to cross. The forecast itself, before the end of 2026, the second public deadline in 2 years, issued by the only team ever to call an eruption 7 months out, has a little over 4 months of life left, and its own authors describe the volcano as not imminent. A sealed rival forecast updates monthly in Zurich and Uppsala, unreadable until the mountain grades it, and the machine recording all of it is guaranteed exactly 25 more months of electricity. That is the complete, honest state of the most predictable volcano on Earth, critically loaded, fully instrumented, publicly scheduled, and drifting off script in the quietest possible way. If you want to watch the ending yourself, and this may be the only volcano story we have ever covered where you genuinely can, the watch list is short, public, and requires no expertise. The daily earthquake count on the University of Washington's live page, below 100 means the long wait continues, a sustained climb through several hundred toward 500 a day, held for weeks rather than spiked for a night, is the forecast's actual trigger condition beginning to arm. The uplift rate, on the Oregon State Forecast blog, updated every few months. Another slide from 4.5 means the deadline is likely dead. A rebound toward the pace of 2024 means the countdown is live again. Those two numbers, together, are the whole game. Everything else, the headlines, the any day now cycles, the anniversary rediscoveries, is noise, and you now know exactly how that noise gets made. There is a third feed worth adding to the list, slower but heavier. The Forecast blog's own cadence. Chadwick and Nooner post every few months in quiet times, March, May, July this year. But the record shows the rhythm quickens when the Volcano does. A new post landing out of cycle is itself information, and behind everything, remember the two dates with no data attached. December 31st, 2026. The deadline expires, and either the forecast has its vindication, or the team faces a third reckoning. And if the pattern of their own honesty holds, they will publish the miss in full at the AGU meeting that same month, and the envelope in Zurich will stay sealed a while longer. Then, January through April of 2027. The only eruption season this volcano has ever used, opening days after the deadline closes. If Axial misses the forecast and then erupts inside that window, it will have been wrong by weeks and right by history. The kind of ending that would keep both forecasting camps arguing for a decade about what, exactly, was learned. It is worth saying plainly why this story earns a place on a channel that usually tracks the disasters that can reach you. We have spent this month on faults that end cities and volcanoes that empty provinces, stories where the stakes are counted in lives and the honest currency is dread. Axial pays in a different currency. Nothing out there can touch you. Every dollar of drama in this story is intellectual, and that is precisely its value. This is what the science of prediction looks like when it is allowed to fail safely. Deadlines posted and missed in public, rival methods racing on live data, instruments fighting for their funding, and a mountain grading everyone on its own schedule. Every future video where a forecast matters, every Cascadia update, every caldera alert, every scientists are watching closely, will be in part downstream of what this harmless seamount teaches. When we tell you someday that an eruption warning somewhere is credible months out, the credibility will have been built here, in the dark, off Oregon. And when it finally happens, understand what you will be witnessing, because it will not look like anything. No cloud, no glow on the horizon, no shudder under any coastal town. Somewhere in a dark caldera, the count on a public website will go vertical. 100 quakes, 1,000, 5,000, the dots marching north along the rift as the reservoir unzips. And a red pressure curve will begin to fall as the floor of the caldera lets go of 11 years of accumulated ocean. On shore, phones will light up in Newport and Seattle at some terrible hour, and a handful of people who have waited a decade will watch a mountain keep an appointment, or break one, in real time. The lava will pave its miles of seafloor in the dark, the microbes will bloom into their snowstorm, and within days the floor will begin, imperceptibly, to rise again. The piston resetting, the next cycle opening, the balloon starting back toward a threshold it will reach long after every deadline in this story is forgotten. Somewhere out there tonight, all of it is simply happening, indifferent to every clock we have set. The pressure sensors are logging their 20-second samples. The red curve is inching along at 4.5 centimeters a year. A few dozen tiny earthquakes will crackle through the caldera before morning, each one a floorboard settling in a house that has been over its load limit since last winter. The camera light is on at the mushroom chimney, the worms are grazing, and the tide is easing its grip on the summit right on schedule, the way it has twice a day for the 11 years, 3 months, and 27 days since the floor last fell. Every instrument agrees, nothing is happening. Every instrument also agrees, everything is in place. That pairing, total knowledge, total uncertainty, is not a failure of the observatory. It is the truest measurement it has ever produced, an exact real-time portrait of the limit of what knowing can currently do. One of two lessons is coming, and the volcano has already chosen which. Either eruptions can be scheduled, and somewhere decades from tonight, a city will empty calmly, months early, because a harmless seamount off Oregon spent the 2020s teaching us how. Or the deepest lesson of the best-watched volcano on Earth is that a mountain with every instrument we own pressed against its skin can still keep its secret until the hour it chooses. Both lessons are worth the price of the machine. Only one question decides between them, and it is the question this whole story has been circling from the first sentence. When the floor finally drops, will the wire still be listening? The forecast expires December 31st. The eruption season opens in January. The cable dies in September of 2028. Watch the count.